When people wonder how telescope data survives space, the honest answer is that at first it didn't, or at least not reliably. Space is hostile in many ways, of course, but in many ways that aren't obvious if you're used to computers and cameras working perfectly on Earth. For just starters, there's radiation everywhere, temperatures go up and down wildly, and there's a ton of distance that stretches out signals until they're barely there at all. And the systems we use today to gather the data exist because early missions failed often enough to teach engineers some very hard lessons. And this all begins with the earliest satellites, like the Sputnik 1, for example. These machines were of course a marvel of engineering, but also were incredibly simple by today's standards. So Sputnik didn't send images or files or anything we'd recognize as data now, it just sent beeps. Like literal radio pulses that told engineers on the ground, hey, I'm still here. And even those signals were fragile. There was pretty much no protection against interference, no way to confirm that what was received was exactly what was sent. If noise were to distort the signal or a transmission just happened to drop out, that information was just simply gone. Of course, at the time, this was acceptable because expectations were low. Those early missions were just experiments, proof that something could orbit Earth and talk back at all, which was very exciting. But as soon as engineers tried to do more than that, obviously problems would pile up fast. Electronics behave differently in orbit, and the irradiation of space would flip bits in memory, which was bad. There was a big issue with temperature changes causing components to just stop working. And of course, a big problem was that the signals would just weaken in general as soon as satellites moved further away. So the engineers and scientists working on these satellites quickly realized that space wasn't just fully empty, but it was actively hostile to these precise signals that they wanted to get down to Earth or up to the satellites. This was an important realization because it shaped everything that followed next. They learned that you couldn't just treat space communication like some very long radio cable as they used at the time. You had to assume failure as the default condition. Any system that depended on perfect hardware or clean signals would eventually break because that just wasn't what was going on. And things became much more serious when missions started trying to leave Earth's general location. A very well-known one is the Voyager probes, specifically 1 and 2. These probes forced a complete rethink of how data survives over extreme distances. So when the Voyager 1 and 2 were launched, engineers knew that they would be communicating across millions and then billions of kilometers, which is the case right now. So signals wouldn't just be weak, but by the time they reached Earth, they would either be completely unrecognizable or would not even reach Earth at all. And at those distances, even the most tiny, minuscule problems would become major threats. A single flipped bit in memory could literally corrupt an entire message. And just even a momentary power glitch in the hardware could literally wipe all the stored data that the satellite had with no way of getting it back. And of course, unless some brave astronaut decides to travel 25 billion kilometers personally, there was no option to reboot the spacecraft or swap out a bad component. Whatever you send out there just had to survive on its own for long enough to send correct data back. And this is where reliability engineering became the entire backbone of this science. They realized that data could no longer be treated as just a continuous stream, because there could be very well a bunch of errors within that. So instead, it was broken down into packets, which are small chunks that could be tracked, verified, and resent if something went wrong. Within these chunks, they added error-correcting codes, which allowed the receiver on Earth to detect and often fix mistakes without needing a retransmission. And the very simple fix to the hardware problem was just that spacecraft were designed with redundant systems, meaning multiple copies of critical hardware and memory would run in parallel. So if one breaks, the rest still work. And just as important, spacecraft learned to take care of itself. If a system detected a fault, it didn't just wait for instructions from Earth of what to do, it would automatically switch to a backup or reset itself or enter a safe mode automatically. The Voyager missions showed that long-lived missions can only even be dreamed about if they constantly expect something to fail and recover without needing human intervention. And this was the correct call because the Voyager is still out there in space, sending signals and receiving them 25 billion kilometers away. Everything we've spoken about just now was pre-digital age. So by the time astronomy entered the digital age, these lessons were deeply embedded in spacecraft design. The launch of the Hubble Space Telescope, for example, marked a very big shift, not just in what we observed, but in how observation itself worked, if that makes sense. Before Hubble, astronomy relied heavily on photographic film. Astronauts would physically retrieve exposures, or observatories would process film on site. That approach obviously just simply doesn't work for space telescopes operating continuously without needing human intervention. The Hubble telescope replaced film with electronic detectors called CCDs. And so instead of capturing images directly, Hubble measured incoming light and converted it into numbers. So each pixel on the detector recorded how many photons hit it over a certain time. So the raw data of these numbers was just a table of values plus a large amount of metadata which would describe the telescope's orientation, temperature, and general operating state, with obviously a lot more extra little details that you'd have to be a NASA engineer to know. It should be obvious why this change mattered, because not only is it just more data in general, but we're also using numbers, and numbers are just amazing because they can be copied, checked, corrected, and reprocessed. If an early Hubble image looked blurry or flawed, its raw data of numbers could literally be reanalyzed years later with better software to get a better image still. So now all the telescope had to take care of was just to send the actual raw data, and Earth-based processing could do the rest, even years into the future. And so this also clarifies the idea that often surprises a lot of people, which is that, again, space telescopes don't actually make images. They collect measurements in numbers, which is called raw data. The images we see are just interpretations mathematically built on, pure Earth. And I don't want you to underestimate the scale of how important this is, because this separation between measurement and visualization on Earth made it possible to extract far more science from the same data. It meant that we could now have a lot more data and a lot safer, but it also meant that preserving the integrity of those numbers became very critical. And so as telescopes grew more complex, so did their independence in space. Modern observatories like the James Webb Space Telescope represent the endpoint of this evolution so far, which is why it was such a big deal. And Webb doesn't orbit that close to Earth. It sits about 1.5 million kilometers away at a certain gravitational balance point. So astronauts cannot visit it, repairs are literally impossible. Every single decision, from mirror alignment to fault recovery, must happen on board and cannot be changed. And so at this point, a space telescope like the James Webb is less like just a camera and more like a robotic laboratory with a camera attached onto it. It monitors its own health, it adjusts itself, and it decides how to respond to problems. But all of this is done for data protection, because data protection isn't something that they just add on top later. It's woven into every single design choice of the satellite or the telescope. So I hope by this point one thing should be very clear, that telescope data doesn't survive space by accident. It survives because engineers assume that space will try to destroy it at every step. So all the systems are designed around that assumption. And so by the time a modern space telescope begins operating, all the big ideas from earlier missions are already baked in. We already know them. But the real magic happens in the details, right? To understand how telescope data survives space, I think we should follow one observation from the moment light hits the telescope to the moment an image appears on screen on Earth. So I mentioned this before, but let's talk about it in a bit more detail. It begins with the light itself. Telescopes do not take photographs in the way a phone or a traditional camera does. When light from a star, a galaxy, or planet reaches the telescope, it strikes an array of detectors. Each detector element, often called a pixel, measures how much light arrives during an exposure. That light is then converted into an electrical signal, and that signal is turned into a number. And what the telescope produces with all of this is a massive grid of values in numbers. Each number represents brightness at a specific location on the detector. Alongside those numbers is metadata, again, when the exposure was taken, the temperature, the exact orientation, yada yada yada. And so this entire package is the raw data. We have no color, we have no contrast, and no visible picture at all just yet. From the moment those numbers exist, even just within the satellite, space begins trying to corrupt them. High-energy particles from cosmic rays can flip individual bits in memory, meaning numbers. And this is very bad because even one flipped bit could corrupt the data altogether. And just the general radiation and temperature changes of space, once again, cause these tiny shifts in hardware behavior that add up to subtle and then more noticeable hardware errors over time, which obviously sucks both for gathering data and for actually keeping the satellite running. But so what do you do about that? If left unprotected, this would slowly degrade stored data until it became useless. And to prevent that, spacecraft treat data as something that must be constantly defended. So memory systems use error-correcting codes, which add extra bits into the system, or extra numbers into the system, to detect and fix small mistakes automatically. And this is done because data is often stored in multiple locations at once. If one copy is detected to change unexpectedly, it's just overwritten by the others. The spacecraft doesn't assume its memory is trustworthy, it checks over and over again and ensures to stay on top of what's real. Even the processors themselves are designed differently from those in consumer electronics. They are radiation hardened, meaning that they're built to tolerate particle strikes without crashing or silently corrupting the data. These chips are slower and less powerful than modern phone processors, but they are far more predictable for their environment. And in space, that reliability is the only thing that matters. So, okay, we have the data safely stored, amazing, but it eventually needs to be sent to Earth. This is one of the most counterintuitive parts of the process. By the time a signal from a distant telescope reaches Earth, based on alignment between the telescope knowing where to point the signal to, right? That's how it reaches Earth. It can be weaker than the background noise of space itself, which is crazy. There's no clean or loud transmission that people know to look out for. Instead, engineers rely on certain mathematics and redundancy to pull out meaning from all of the noise that they receive. So I mentioned that data is broken into packets before transmission, and that each packet includes information about where it belongs in the overall data set, along with checks and error correction bits. The telescope takes these packets and turns them into radio waves towards Earth, where we have large antennas listening for them. On the ground, the signal is processed by systems that look for patterns matching the expected transmission, even when those patterns are barely distinguishable from literally just normal noise in the atmosphere. So once radio waves arrive that actually form a real packet, it isn't just trusted automatically. The ground system checks whether the packet is intact. If errors are detected and can't be corrected, well then the packet is just rejected. And if a packet is missing entirely, the system knows exactly which one didn't arrive because of their order metadata. And the beauty of how everything is set up is that when possible, the telescope is asked to send the missing or corrupted pieces again. So literally like a puzzle, we already have all the other packets, but we're just missing packet number 42, so that's the packet we need from you. And so only once all of these pieces of the puzzle pass all verification checks are they accepted and stored. This is how it's possible to recover usable data from signals that seem impossibly faint. The process isn't about hearing the signal clearly or trying to make the signal louder or whatever, but it's all about recognizing the structure and consistency over time. And so with enough verification and asking the satellite to send data again, even extremely weak transmissions can be reconstructed very reliably. And once we have this data safely on Earth, a new phase begins. This is where raw measurements turn into something humans can interpret. The ground-based processing systems remove known sources of noise caused by just the general Earth atmosphere. They're aware of certain distortions caused by the instruments and correct those as well, and they align multiple exposures of the same object together, which is just what's known as exposure in cameras. But for satellites, this also means that data is taken in different wavelengths, including infrared and ultraviolet that humans can't see, and is combined together in very meaningful ways to then create things that we are able to see. So again, let's take color. Color is assigned based on scientific choices, not what on the telescope saw, because it doesn't really do that. So these systems adjust the contrast of the image to reveal faint structures of space. Details are also sharpened very carefully to avoid showing features that aren't really there. And every single step is carefully documented so that scientists know exactly how the final image was created. So every bit of data that we receive from these satellites really can just be looked at as one big puzzle, which is sent over by the telescopes and which is then put together here on Earth. So I hope this video showed you that the most important thing to understand is that these beautiful images people associate with space aren't even direct outputs. They're just a final layer of interpretation applied to carefully preserved data from telescopes, using a lot of super smart and complex math equations. So what the telescope does is simply measures some data of the universe, and our job on Earth is to make those measurements understandable and visualizable to humans. So then when someone wonders how telescope data survives space, it is a very layered answer, right? It survives because engineers learned that early space is unreliable. It survives because every system assumes errors will happen and plans for them beforehand. It survives and stays consistent because data is duplicated, checked, corrected, and verified at every single stage, and there are no slip-ups. And it survives because the way this data is collected allows scientists to, again, extract meaning long after the photons themselves are gone. In 10 years, we could revisit the same data we have right now to create clearer and better images. But the weird and the short answer for the original question is that we just got better at refusing to trust data that comes from space, and also reduce the chances of corrupted data getting through to a near 0% chance, giving us beautiful 8K or even more images of nebulas and whatnot. So I hope you enjoyed this video. Do leave a like and share, and leave a comment of what you just thought of this video and what you think of this topic in general. And of course, thank you for watching.